So in this video, I'm going to talk about retransmission strategies for transport protocols in order to achieve reliability, in particular for sliding window protocols. The basic question is we have, with some sliding window reliable transport, a window of packets that are in flight. Say 1, 2, 3, 4. And we're using cumulative acknowledgements. And so all we get is something back such as ACK1, ACK2, ACK3, ACK4. Just the last byte that was successfully received, or the last packet that was successfully received. We're maintaining a retransmission timer for each of these packets based on when they were sent, and essentially maintaining a conservative estimate of if we haven't received an acknowledgement for the packet by this time, then this means that it is almost certain that the packet was lost, and so we should retransmit it. And so the question is, given this set of parameters which are generally used for reliable transport, how is the protocol going to behave? What is its retransmission strategy going to look like? So we'll see is that there are essentially two strategies you end up emerging from different protocols. The first is we call go back N. So what we think is that go back N is a very pessimistic approach, or pessimistic behavior, which is that if a single packet is lost, then we're going to retransmit the entire outstanding window of packets, go back N. So if the window of size N, we lose some packet, we're going to go back N transmissions, retransmit all of them. The second is selective repeat, which we think it is optimistic. So where go back N assumes that if one packet is lost, all of them are lost in the window. Selective repeat assumes that if one packet is lost, only that packet was lost. So in selective repeat, if we lose a packet, it's not acknowledged, we'll retransmit that packet and only that packet. So let's look at what go back N appears like, or what's the behavior that you see. So let's say that we have a window of size equal to 4. And so the sender sends packet 1, 2, 3, 4. And packet 2 is lost. So here are our 4 transmissions. Well, in response to packet 1, the receiver is going to send acknowledgement, and acknowledgement 1. But it's not going to send acknowledgement 2. And so what will happen is at some point, we're going to have a retransmit timer go off. And then in a go back N protocol, what the sender is going to do is it's going to retransmit the entire outstanding window with some kind of timing. And so don't forget, the window is going to include 5 because in response to this ACK1, it can send 5. But so the transmitter, seeing the packet 2 was lost, is going to assume that the entire window was lost and retransmit the entire window. This is very conservative, very pessimistic. So now let's see what a selective repeat protocol will do. So again, N equals 4. We transmit 1, 2, 3, 4. 1, 2, 3, 4. Packet 2 is lost. Packet 1 is acknowledged, which lets us send 5. In a selective repeat protocol, the transmitter is going to retransmit 2, and then we'll continue execution and transmit 6, 7, 8, 9, ... So it'll retransmit only the packets that were not acknowledged. So one question that comes up is why, given the selective repeat sends fewer packets, why would you ever want to do go back N? Well, there are a couple of reasons. One is that selective repeat, if actually all of those packets were lost, if packet 2, 3, 4, that packets 2, 3, 4, and 5 were all lost, in order to do each of these retransmissions involves timers and round trip times, so it can be much slower. If there's a burst of losses, a selective repeat protocol will often be slower to recover, as opposed to go back N, who assumes that all the packets are lost, it retransmits all of them, and it can get going faster. And so there's a trade-off here between sort of the amount of data that you send, how quickly you send it, and then how much of it is wasted versus the speed of recovery from significant errors. So let's walk through 2 example transport protocols and their configurations and see how they behave, what happens. So in this first one, our sender has a window of size N, and let's say that N is equal to 4, just like the prior examples. And the receiver has a window of size 1, so the receive window size is 1. So based on this, is the protocol going to behave as go back N or as selective repeat? Well, so let's walk through what happens. So the sender, let's say, is going to send 1, 2, 3, 4. 1, 2, 3, 4. And let's say that packet 2 is lost, so it doesn't arrive. Well, the receiver is going to acknowledge 1, which will allow the sender to send 5. But the receiver is not going to acknowledge 2. Now, at some point, 2's retransmission timer is going to fire, and it'll retransmit 2. But the thing is that because the receiver has a receive window size of only 1, it has been unable to buffer packets 3, 4, and 5. And so when it receives packet 2, it's going to act 2. The sender has not received an acknowledgement for 3. It's going to have to retransmit 3. And then the receiver can acknowledge 3. At some point, the sender can then start using its full window again, but the point being that since this first 2 was lost, 3, 4, and 5 couldn't be buffered, the fact that the receiver has a window size of only 1 is going to force the sender to retransmit every single packet in the window. So we're going to see that this behaves as go back N. So let's see a second example. So in this case, the sender has a window size of N, and the receiver has a window size of N. And let's say that for both of them, just again for simplicity's sake, this is of size 4. So in this case, will the protocol be go back N or selective repeat? So let's walk through what happens. We have again 1, 2, 3, 4. 2 is lost. So we get an acknowledgement for 1, ACK1, results in packet 5 being sent. Then at some point, 2's retransmission timer fires. And so we resend 2. Now the receiver has been able to buffer these packets because it has a window of size N. And so it had 3 packets buffered. It can then, so here is its buffer. It had packets 3, 4, and 5. Packet 2 arrives. It can then acknowledge 5. So it might be that the sender was a little aggressive. Maybe it did retransmit 3 or 4 or something. But the point is that it doesn't have to. For this to operate correctly, if, say, it just waited for those retransmission timers or it did slow retransmissions, etc., that the sender is going to resend only packet 2, only the outsending packet that was not acknowledged. The rest have been buffered to the receiver. And so we see that this behaves as selective repeat. So when you're implementing transport protocol, say when you're doing lab 2, one thing you want to think about is how you handle your retransmission. So one of the really important things is that you don't retransmit earlier than you should, by which I mean it's not okay to, say, start a retransmit timer based on packet 1 or packet 2, and then when 2's retransmit timer fires, retransmit an entire window. Because it could very well be that 3, 4, and 5 have been correctly received or something has happened, but you're going to retransmit them anyways. You're very aggressively putting additional packets in the network. You're inflating the number of packets in the network beyond your window size. 3, 4, and 5 could still be in the network, yet you're putting additional copies of them. So in that way, you want to be careful about the number of packets you put in the network. You be careful about your retransmission policy. And so we'll see, what you can see is that on one hand, you can assume, try and be very conservative and say, look, if one packet was lost, I'm going to assume that the others were lost, and then I'm going to retransmit the entire window with a go back N policy. That'll happen if, say, your receiver has a window size of only 1. Or you can maybe be a bit slower and say, look, one packet was lost, I'm going to wait for round trip time, transmit that, see if I get an acknowledgement, see what the acknowledgement puts me, and then perhaps just do a selective repeat and transmit only the packet that needs to be transmitted.